Hello! Welcome to REAC 2024, everybody. My name is Kevin Todisco. I'm a principal software engineer at Blizzard working on graphics for Diablo IV, and today I'd like to present the work we did to bring ray tracing to the game. I also want to apologize for not being able to be here the day of the conference to answer questions, but my colleague, coincidentally named Kevin, has graciously offered to stand in to field questions at the end of the talk. The advent of real-time ray tracing is a really exciting opportunity for graphics on Diablo because of how much it can add to pretty shots like this one here. But the major challenge we faced was that the game was not art-directed nor architected with ray tracing in mind. As I hope to show, this has a significant impact on the decisions surrounding the feature and on how it is implemented. Here's a general outline of what lies ahead. I'll start at the high level, how ray tracing came to be in the project and the eventual decision-making process for determining how we would utilize it and what features we would target for release. I'll then dive into the low-level details of what it took to implement, in particular how the architecture was influenced by the challenges of adapting it to the technology we have. Then I'll come back to a higher level again and talk about what implications it had for the content and how we found the middle ground that satisfied all our constraints. And finally, I'll give some last thoughts about the work as a whole. I'll caution upfront that this is not a comprehensive deep dive into ray tracing in the game. A few details about how things work are omitted. Instead, this talk aims to highlight the evolution of the feature and how it and the decision-making behind it are influenced by factors like art direction, technology direction, and the engine that it's being added to. Ray tracing's inclusion in Diablo can very much be separated into two stages: research and development and full production. I think that the complete picture is probably more complex than that, but separating it into two distinct times is best for our purposes here. The first inclusion of ray tracing was done with some general intention to ship it. Someday. It was an engineering-driven experiment done well before Diablo IV had a release date and was tackled largely to incorporate the technology so that perhaps it could be utilized to a greater extent later in development. It was, by all means, not a shipping solution, but it did work. The implementation sat around for a time, atrophied slightly, and then as the release window for the game came into focus, it gained renewed attention. This is a feature we wanted to include in the game. The question became what kind of work would be necessary to do it. And in addition to our independent intention to add ray tracing, we also developed a partnership with NVIDIA, as the game would obviously be a fine addition to the lineup to promote their ray tracing technology. In an extremely watered-down view of things, this feature goes from a side project, taken on almost solely by one engineer, and turns into, okay, how do we actually get this thing out the door? Just about all of what I'm about to cover in this talk is around that second part. How do we get this thing out the door? Some of what follows may sound like they were considered in sequence, but that's mostly to help with the presentation. There was often a lot of overlap of the development of different pieces. We'll start by talking about the decision-making that went into how we incorporate ray tracing. When we look at how to implement a feature like this and how it fits into Diablo IV, there are a lot of factors to consider. What artistic goals can the feature support? What kind of experience do we have on the team? What kind of support do we have from the art team? How much time do we have? How much performance headroom do we have? Our inclusion of ray tracing would be motivated by keeping up with technology trends and shaped by the balance between resources available to invest in new technology and resources needed to complete the game. The game is not art-directed with ray tracing in mind. One major reason for this is the variety of platforms we support, which include previous generation hardware, the Xbox One and the PS4, which do not have any hardware ray tracing support, and our PC min-spec is set well before dedicated ray tracing hardware was released. Our art team was not prepared for the game to diverge visually, at least significantly, with ray tracing enabled, so much of the direction was to maintain the existing look of the game and merely have it augmented. Tastefully, if you will. Ray tracing was looked at, in part, as a way to get rid of undesirable artifacts like light leaking. The feature would be considered a success from art's point of view if the visuals remained as they were but with fewer artifacts. If you're familiar with ray tracing work in other titles or in the differences between a ray trace scene and one lit with traditional baked lighting techniques, you'll know that the two don't often match up, and so the challenge to meet art direction becomes clear. Given the artistic parameters within which we need to work, we then have to consider the kind of resources we have available to do it. I just talked about how we would have little art support because content was not intended to change, but what do things look like for engineering? Time is a big consideration, and so is team experience. We had no prior experience shipping a real-time ray tracing feature and no formal experience working with real-time ray tracing in a AAA game engine, let alone on each of the different platforms we plan to release on. This itself is an important consideration because for our target platforms, there are not just one, but two ray tracing APIs to work with, DirectX ray tracing and PSR for the PS5. Ultimately, the release of ray tracing in the game was deferred until after game launch, allowing the team to focus on shipping the title first, and then adding new technology after. And on the performance front, we had to establish how ray tracing would fit into our landscape of platforms and specs. Here are the specs that Diablo IV launched with. The previous generation of consoles running at 30 frames per second in 1080p, the current generation of consoles running at 60 frames per second at 4K, a lower internal resolution upscaled with FidelityFX Super Resolution 2 to an output of 4K, and PC at any range in between these or even above. Because these are the specs the game was designed to ship with, you'd be correct to assume that content at release pushed the platforms right to the limit. What that leaves us with is no available overhead to fit in a resource-intensive feature like ray tracing, while still maintaining 60 FPS on these consoles, without needing to make reductions in other areas at least. So the next obvious choice is to introduce another mode of execution, a quality mode, which could not only include ray tracing but also bump the quality level of several other graphical features the game offers, and in turn lower the target FPS to 30. On the whole, when we think about the strategy that has the biggest impact on the game, it's one which solves the problems that art looks at it to solve, one which offers an enhancement to the visuals of the game, and one which maximizes the cost of implementation to get the most benefit in both of those categories, all without changing too much to run afoul of direction, but still changing enough to be looked at as a desired upgrade. So the tried and true techniques of shadows and reflections are the best fit in the face of all these criteria. They incur the least R&D costs because they are already known quantities in the field of ray tracing and perhaps the two most exercised applications of it. When it comes to content, shadows could be considered the most important for a game in the style of Diablo. It's dark, gothic, and is meant to evoke feelings of horror and the occult. The game therefore is serviced by having high fidelity and high detailed shadows that drive home that mood. Reflections, on the other hand, are less thematically relevant, but extraordinarily straightforward in terms of implementation. Fire a ray into the scene and reflect it. At the outset, the expected time investment to stand up the technique is very little and has the least unknowns. It's perfect for a team with little ray tracing experience and less room to try something new. Finally, these techniques were chosen in some part by the evolution of ray tracing within the engine itself. As I mentioned in the beginning, it was first added on the side by one of our engineers not long after the announcement of real-time ray tracing and the release of the DXR API. It lived in the engine for some time before being given the attention of a shipping feature. The blueprints for shadows and reflections were there, completing them became the goal. There is still more to figure out though because these features are meant to ship on a few different platforms with varying capabilities. They need to be broken down further in some way to make them scalable. We arrived at these tiers of each feature. For shadows, we have low, medium, and high options, which each add a new element into the mix. At the lowest tier, we only ray trace the directional light. It's therefore only active during the daytime and outdoor scenes. At medium, we mix in one punctual light source, the player light. This means that ray tracing is now active at nighttime and in dungeons, and augments the one punctual light you are sure to have around you at all times. Finally, high is the enthusiast tier. At this tier, we ray trace every eligible light, that is, any point or spotlight in the scene that is flagged to cast shadows will be ray traced. For some content, it is a pretty significant jump in the demand on the hardware. We would frequently refer to this as the I have a 4090 tier. Reflections were broken down into just two tiers, low and high. Low is a single ray solution treating the reflective surface as a mirror and only factoring in the surface normal, while high can fire multiple rays based on the roughness of the hit point. Low uses a simple blur as a post-process effect on the result, while high uses a higher quality denoise operation. The difference between the two is more subtle than with the shadow tiers. Okay, let's talk about implementation. Fair warning, for time purposes, I'm not going to give an overview of real-time ray tracing APIs here and how they work. Some familiarity with them will help, but I will provide very brief explanations of terms where I can. A major feature like this, I think intuitively, is going to touch many parts of a rendering engine. If I were to map out the components of our rendering pipeline in a very generic way, I'd make something like this here. And here are the parts that ray tracing directly impacts. The most notable omission here is art. A reasonable expectation would be that ray tracing would greatly impact the art in the game, but as I explained before, in our case it does not. Our goal was to work to minimize impact here, but many other components do change. And by the end of the whole effort, even our raster techniques would be affected, which maybe one wouldn't expect up front, but I'll cover this a bit later. I'll begin by talking about shaders. On Diablo IV, we don't use a bindless resource paradigm, instead a more traditional binding model on a per-draw basis. To support ray tracing, we take advantage of register spaces and access all hit group textures in register space 1. The vertex and index buffers for barycentric calculations are bound in space 0 after our traditional raster pipeline bind locations, beginning at register 52. Since ray tracing does not provide any means for vertex manipulation, skinning and other vertex operations are pre-computed on async compute early in the frame and then cached for later use. This was work that we had tackled actually independently of the ray tracing effort, and it was simply serendipity that it was already done when the time came to leverage it in the ray tracing pipe. Interestingly though, only pre-computed skinning results are used by default in the game, while pre-computed speed tree is only used when ray tracing is on, and the reason for this was that performance results using pre-computed speed tree versus speed tree evaluated in vertex shaders were mixed on consoles, so the decision was made not to switch paths. Of course, needing to pre-compute and store all of this vertex data has an impact on memory, so that's something to keep in mind when it comes to fitting into our performance headroom. We have a shader graph system which allows our technical artists to create custom shaders for the varied materials throughout the game. The shader graph system is fairly standard, so I won't really go into much detail here. The graph itself is processed during the build into HLSL that represents the body of a complete shader. It is joined with a header that defines the inputs the graph is allowed to manipulate and the outputs that the graph writes to which are based on the paths that it's intended to run in. Extending this for ray tracing is fairly intuitive. The HLSL generated by evaluating the graph can be transplanted into a different type of shader, a ray tracing one. Could be an any hit shader or a closest hit shader. The header is now the hit group definition. A hit group is the collection of material and shader state for a particular object in the ray tracing scene. Then there's some boilerplate code to read from the vertex and index buffers, calculate barycentric coordinates, perform some texture samples, and then pass them to the graph body, just as if it had received them from interpolators in the traditional raster pipe. For output, the graph results can be connected to more boilerplate code that performs things like an alpha test for shadow rays, or lighting calculation and payload merging for reflections. For the majority of shaders, there is only one path that the shader belongs to, and so only one graph for us to choose from when deciding which to incorporate in the compilation of the graph for ray tracing. However, for a handful of shaders that are multipass, the heuristic is not as easy. In this example, the phantom enemies are drawn with a multipass shader, and the first pass only writes an alpha value. It's not suitable to pick for ray tracing, and as a result, these enemies would appear with no color, as seen here. No good heuristic exists to programmatically determine the intended pass to use, so our solution was simply to add a means of selecting a specific pass in the graph to compile for ray tracing, and manually selecting it for multipass shaders. To help validate the correctness of ray tracing versions in our shader graph, we have a debug render mode in which all primary visibility in the game is ray traced, so this is it in action. Fully ray traced Diablo IV. When it comes to generating work for a frame, we have one render thread and 4 worker threads. Diablo does not use a task graph style system. Instead, the work is manually separated amongst render workers. Generally, each worker is given a specific chunk of responsibility that corresponds to a distinct serial block of the frame. For example, one worker generates the commands for early work like shadows, another generates work for rendering the G-buffer, another scene lighting, and the last one post-processing. Each worker maintains two state machines. One of these state machines is stored in global space and contains high-level engine-specific information about the state of the graphics pipe. Examples might be what the current parameters of our two types of fog are, what the state of the lighting pipeline is, what the state of the sky is, and so on. The other state machine is a thread local storage and describes low-level details such as what command list object is currently active and what concrete resources are currently bound, and what values are contained in each constant buffer. Traversing over the scene involves modifying both high-level and low-level state. Typically, high-level state is modified first, and then the push of a draw call flushes the high-level state into low-level state, and then flushes the low-level state to the command list. The most important takeaway here is that this setting, transferring, and flushing of state is a very hot path. Being the main architectural paradigm of the core graphics engine, it meant that the ray tracing work generation would naturally follow this path as well. To support iterating over objects earmarked for ray tracing, a new thread-local, low-level ray tracing state was added per render worker. It tracks things like currently bound hit group resources, the current pipeline state object and if it's being compiled or is available for use, the active shader binding table, and the active top-level acceleration structure. That structure, the scene into which rays are fired, or TLAS for short, is built in its entirety on a single render worker. It can't be built across multiple threads, but a single render worker could build more than one TLAS. It just has to do so serially. Pipeline state object creation is deferred. If the PSO is not ready when we want to use it in a ray tracing technique, we simply don't perform the technique for that frame. For both shadows and reflections, we're able to fall back to raster in this situation until the PSO is ready for use. And on PC, which supports incremental build of PSOs, we use that. The other thing to talk about real quick is how scene traversal works in the engine. At a very high level, we bucket objects in the scene into different display lists. These can be techniques like the G-buffer, transparent pass, cascade shadows, punctual light shadows, and of course, ray tracing techniques. Display lists are named enumerations, so they have a backing type, which is a UN64, meaning we can support a maximum of 64 of them. We can support a maximum of 64 of them. The backing type only allows for 64 things. Each display list has a visibility test associated with it, and objects with materials or specialized logic that put them into a display list run that visibility test. The list of objects included in the display list for the frame is then iterated over to generate draw commands. For ray tracing, each technique follows a common pattern of operations. First, we iterate over the objects in the display list to determine all of the ray tracing shader libraries contributing to the shader binding table, this frame. This helps us assemble or update the ray tracing pipeline state object. Then the objects in the display list are iterated over again to build the top-level acceleration structure and populate the shader binding table. These two steps have to be written in such a way that they produce identical iterations. A mismatch would cause an object to point at the wrong material values, or worse, an invalid shader binding table entry. So let's walk through an example of scene traversal to construct a shader binding table and fill out a top-level acceleration structure. As we iterate over the first object, all of the object's relevant state is updated in the thread state machine. We then invoke the function call to add the instance to the shader binding table and the TLAS. This flushes the state machine, which fills out the hit group entry in the shader binding table, and then adds the BVH for the object to the TLAS with a reference back to the new hit group entry. We then repeat this process for each object following. It's worth pointing out that each individual object here is getting a unique hit group entry in the shader binding table. And this becomes notable because ray tracing will naturally involve processing many more objects than the primary camera frustum would normally, considering, for example, the objects that are behind the camera for reflections. There's simply going to be more objects processed. This puts a strain on the existing architecture, as the state machine population and flush were designed and exercised to process a certain number of objects to hit a target frame rate. And we've now doubled, tripled, or maybe even quadrupled those numbers in some cases. The cost on the CPU becomes very high. Considering how central this whole mechanism is to the engine and how ray tracing is coming online after shipping the game, changing this architecture by, say, reworking the work distribution model or the state machine mechanism would be a massive undertaking. Instead, our best option is to optimize by changing the hit count rather than the architecture. Lowering the temperature on this hot path should alleviate the performance bottleneck. The first major area that can be addressed is something I alluded to earlier. Each individual object is getting its own unique entry in the shader binding table, regardless of whether it shares materials with other objects in the bucket. As a result, we must populate and flush the state cache for each object rather than each unique material in the scene. The intention, of course, is for hit groups to represent material state for multiple instances of objects, just like we do using raster commands like draw instanced. So we did just that. In the new scheme, as groups of objects are found that share material state, only the first object is processed in order to populate the state machine. Then the remaining objects are gathered and a routine invoked to add these multiple instances under a single shader binding table entry. The second major area we can tackle to reduce the hit count is lowering the number of objects that reach the display list, and this is determined by a visibility test. Both reflections and shadows, in this case punctual light shadows. Directional shadows are much more well-defined in terms of what their content should be and will be a very close match to cascade shadow list for raster. Both techniques started with very naive culling techniques, which more or less considered a large number of objects surrounding the player and the camera. Now, our game camera is fixed, so one might assume that we could use this to our advantage for a technique like reflections. And indeed, we try to, but we also have to consider other camera situations like in-game cutscenes and points of interest. Instead of trying to maintain unique approaches for each possible camera scenario throughout gameplay, we opted instead to try to formulate a generic approach that would still achieve a reasonable minimum of objects captured. The initial algorithm for reflections could be seen as a collection of objects in a radius around the player, but specifically it was a wide orthographic projection around the player, which would filter out objects that projected to too small a size. This might be the difference between 12,000 objects and 8,000. We have a lot of small objects. But can we be smarter about how we choose what to include? The method we switched to was inspired by the idea that we have a fixed camera during gameplay, but is also approached in such a way that it can suit any camera used in the game, including cutscenes, at least without any evident artifacts. We start by observing that, much like importance sampling would dictate, a great majority of the rays reflected to the camera are going to come from the ground, from the opposite direction of the camera forward reflection. So we can take the camera forward, reflect it off of the ground plane, and extend it out some distance. We chose a percentage of the main camera's far plane. To obtain the origin point of a new frustum with which to call for reflections. The size of this frustum itself is also a percentage of the main camera frustum, and it, as well as the field of view, was chosen through manual tuning. As for punctual light sources, we initially considered every object within a wide radius around the player. But this can still pull in a number of objects that are not going to fall under the influence of any particular light. So, we introduced a narrow phase culling where each object is tested against the bounds of each punctual light being ray traced, and anything unaffected is still culled. Now, this does mean that a single light is ray tracing against all of the objects intersecting other lights, not necessarily near the one that's being traced. But having made all these changes, we saw some very promising savings. They depended heavily upon the scene composition and complexity, but usually ranged from sizable to significant. For reflections, it was an average of 2,000 objects per scene culled from the top-level acceleration structure, which represented a 20 to 33% reduction in the number of objects previously added to the TLAS in those scenes. For punctual light source shadows, the savings were much more significant. In some cases, we saved 20 milliseconds. Now, this was largely due to the fact that in outdoor scenes during daytime, there are no punctual light sources active, only the sun. As such, the narrow phase culling would reduce the set of objects to be included to 0, so no time would be spent processing them at all. The very nice thing about this is that it naturally excludes TLAS building for punctual light shadows without any specific code that circumvents them by monitoring for specific game content. But even in addition to this large savings in outdoor daytime scenes, scenes with active punctual light sources saw significant savings as well. Most of these savings came from densely packed cities and towns in the game where punctual light sources and many set pieces are abundant, but even in outdoor scenes, the presence of just the player light had previously caused many objects in the area around the player to be considered, and narrowing that set down to just objects very close to the player can save a lot of time. So next we'll talk about the implementation that manages bounding volume hierarchy, or BVH data. Every object that is to be ray traced needs a BVH to represent it inside of a TLAS. Diving into this system requires us to first cover Diablo IV's geometry organization, because as we'll see, this will have a great influence on how we approach managing BVH data. Every object in Diablo is represented by what we call an appearance. In practice, a serialized appearance has a lot more nuance than I'm going to cover here because it's just less relevant to the talk. It contains other concepts like level of detail and substructures underneath that aren't as important here. But at the core, it contains blocks of vertex and index data. And then a series of smaller subobjects, which are the smallest unit of geometry in the game. Each subobject can be drawn with a different material, and it refers to a portion of the vertex and index data contained within the monolithic buffers of the appearance. When considering how to approach managing BVH data, the first approach taken was influenced by the idea of this monolithic vertex buffer contained within the appearance. We can create and maintain a corresponding monolithic data buffer to hold BVH data. And just as the subobjects refer to portions of the vertex and index buffers, they will refer to portions of the BVH buffer for their acceleration structures. Implementing this is fairly straightforward, and is exactly where we started with the initial prototype of ray tracing in the engine. New fields are added to the subobject structure for the size of the BVH and its offset into this monolithic buffer. The important thing to note here, because it's going to become an issue later, is that because subobject is a serialized object, written at data build time and loaded at runtime, its data is technically immutable. Now, we abuse this slightly by creating a singular allowable time to mutate the data on load, at which point the BVH buffer for the appearance is allocated, BVH is created, and offsets recorded into the subobjects. To manage the monolithic BVH buffer, we define a parent structure that actually maintains the first class buffer object and then tracks some state for it. We also added some ad hoc support for compaction. I'll explain what compaction is in just a moment. The compaction map is a remap of each subobject's offset to another newer offset that represents the offset of compacted data. Note that in this scheme, the subobject's idea of where its BVH data is never changes, it's immutable. Instead, this new value tracking it is introduced elsewhere, and in the event that the BVH buffer undergoes compaction, we have to be careful about where we read our offset from when obtaining the address for a specific BVH. Right, so what exactly is compaction? When creating a BVH, one initially passes the geometry to build it into a size estimator API. The size returned is an upper bound on how large the resulting BVH may be. Its real size can't actually be known until the BVH is really built, which is a slower operation. And so we allocate the upper bound for the BVH build. Let's call it here 1 megabyte to make the example easy. We then build the BVH and it populates in the buffer at its real size. There's then another API call which can be used to query the real size of the BVH. And once we have that value, we can allocate a new buffer of exactly that size and copy the built BVH object from our first buffer to our second and discard the original. And just like that, we've saved 600 megabytes. The sizes saved are dependent on GPU architecture, driver implementation, and the complexity of the object, but oftentimes they can exceed 50%, so it's very much worth doing. Now, back to Diablo. When we took all of our eligible assets together in our ray tracing prototype, so that's static geometry, skinned actors, and speed tree assets, the total amount of BVH memory often exceeded 5 gigabytes. That's almost certainly not going to do on PC and definitely not going to do on consoles. Though consoles do not retrace speed tree objects, and those are the majority of our memory, they don't ray trace them for memory reasons, but the differing architecture on the consoles compared to, say, PC graphics cards can inflate the BVH sizes for both static and skin geometry. I digress. Now, I just said a very large portion of this memory is speed tree, and that's due to the heavy instancing of foliage in the game. All trees and bushes have unique animated data during the simulation, so each one needs to be represented by a unique BVH, and that explodes very quickly. Compaction is going to be our first line of defense against this high memory cost. But the problem we have is that it's not very well supported by our initial architecture. How is that? So if we recall, I mentioned that the BVH offset and size that are stored on a subobject are immutable, and they are used to point to where the BVH is in GPU memory. If anything about the location of the BVH changes, say from compaction or copying it to a new buffer, then the old data is invalid and we have no way of updating it. Now we do have that ad hoc compaction support that was added that would suffice for some classes of objects, but being as it introduced the need for a conditional branch for every query of the location of a BVH and also created stale data in the subobject, it was both difficult to maintain and somewhat difficult to understand for a new maintainer. So it's time to refactor. The first of two significant refactors to the architecture behind BVH management replaced the immutable offset and size on the subobject struct with a segment integer. This represents the index of the subobject's BVH within the parent struct's list of BVHs in its monolithic data buffer. Just as before, this field will be filled out on load, but now since we never have a restructuring of geometry data after we load an object, the value itself is never going to change and is thus fitting for an immutable field. The parent struct gains two new fields, the number of sub-BVHs being managed by it and an array of offsets, one for each BVH in its monolithic buffer. Doing this helped the maintainability of the BVH management code, but it did not completely address compaction problems. It was merely a step along the path to get there. Now, since we are maintaining all of these structures in a monolithic buffer, this introduces a requirement that all BVHs within that buffer need to be individually built before the overall buffer can be compacted. A key reason for that, especially for dynamic objects, is that we cannot be completely sure if an individual BVH is going to be built eventually or never. We may attempt to compact the monolithic buffer after only one sub-BVH is built or after a number of them are built, only to find that another was built during that time and then have to compact again. Each of these operations would allocate a new buffer and perform a new copy. Not very ideal compared to the theoretical best of only allocating and copying the one time we absolutely need to. So if even just one of the sub-BVHs is never built, we are not able to compact any of the others, and the monolithic buffer remains at its original size. The potential savings from compaction are left on the table. And just as it happens, many appearances in Diablo do not necessarily activate all of their subobjects at load, since the subobject system is used for variable appearances in the game. Many of our dynamic objects, speed tree included, were ineligible for compaction due to this, and simultaneously represented the vast majority of our BVH memory. So, it's time to refactor again. The major change in the second refactor is a departure from the monolithic BVH buffer into individually allocated BVH buffers. A new struct is introduced to manage this buffer, and some state is moved from the parent to the child struct. The parent struct no longer has to track a list of offsets. Instead, it just has a list of BLAS. This new scheme does an excellent job at allowing any BVH to be compacted. It's now neatly individually managed so that the moment it's built, the real size can be queried and compaction can be performed. But there is a new downside, specifically on PC. DirectX requires that any buffer object allocated on PC has a minimum size of 64 kilobytes, and BVHs are typically much, much smaller than that, sometimes on the order of only a few hundred bytes. With each individual BVH being represented by an individual buffer, there's potentially hundreds of extra megabytes being allocated and never used. Even compaction makes no difference because the compacted buffer is still going to be a minimum size of 64 kilobytes under the hood. So the next step here is paging memory. By allocating memory pages and distributing portions of those pages, the minimum size requirements of buffers is no longer a problem. The page is a multiple of 64K, and BVHs need only be aligned to 256 bytes. As we had a partnership with NVIDIA for ray tracing, we got their help and used their RTX memory utility to manage the paging. It was simple to add and allowed us to implement a custom backend that would integrate with our engine's low-level graphics API abstraction layer. Code-wise, the change at this point was very, very straightforward. Instead of our engine's individual buffer type, the BVH object had a sub-allocated block of memory from RTX-MU. So where did all this refactoring and paged memory actually get us? When the dust settled, a typical scene in the game went from over 5 gigabytes of BVH memory to something around 1.5 gigabytes. It's a remarkable improvement, but it still isn't totally ideal. So are there any other parts of the engine architecture we can look at that might be inflating the used memory? We next turned our attention towards asset streaming. At any given time during the game, there is a lot of stuff loaded around your character. Loaded, but not necessarily seen or even instantiated. The streaming distance tends to be much larger than the bounds of the top-level acceleration structures we're going to use for our ray tracing techniques, especially the narrower bounds created by the improved culling techniques that we covered earlier. Now, as mentioned before, skinned objects in SpeedTree make up the majority of BVH memory, and these are dynamic objects. I haven't explicitly mentioned it before this, but in our ray tracing implementation, dynamic objects only update their BVHs if they are included in a TLAS, meaning they've passed the culling phases at that point for some active technique. This gives us concrete information about whether a BVH is actually going to be used in a frame, in a trace, and as such, would therefore need to be built. So we can defer building BVHs for dynamic objects until they are actually included in a TLAS, rather than on load. A rudimentary garbage collection system is also added to reclaim BVHs that have not been used for a short time, around 10 frames. With this new strategy, we go from having 1.5 gigabytes of BVH memory in representative scenes to only 250 megabytes. Much better. It's at this point I would also mention that with the design having gone from prototype to shipping solution, this change was much, much easier to rapidly test, implement, and distribute. A quick note on consoles, because BVH memory there is slightly different. Consoles offer the ability to build BVHs offline, which can give better memory and trace efficiency because the offline environment can spend more time optimizing the BVH build for these qualities. Diablo IV builds BVHs for all static geometry offline for Xbox Series X and PS5, and the total size of this data when compressed is around 5 gigabytes for each platform. We also elected not to use RTX-MU for consoles because consoles do not have the same memory alignment requirement as PC from a memory management perspective, and it was more suitable to use our internal engine systems in this case. As far as how data was serialized, vertex and index data is tacked onto the end of a serialized appearance file in a big blob. So following this example, BVH data is added in another blob at the end of the file after that. Serialized subobjects within the appearance data point to this data with offsets so that the appropriate portion of the blob can be deserialized at load time. I also want to speak quickly about compaction of dynamic BVHs, or those which are updated as the geometry they represent is animated. While working on this, it became evident that there is a misconception that this isn't possible. As it turns out, updating a BVH merely adjusts the bounding box extents in the internal structure, without actually modifying the number or connectivity of the bounding boxes, whereas refitting a BVH is akin to building it anew. Update will not alter the BVH size. Therefore, BVHs which only call update are still eligible to be compacted. Now there is a trade-off here with build quality. As vertices drift further and further from their original locations the BVH was built with, the quality of the BVH will degrade and tracing it will become less efficient. So the decision point becomes whether to accept the potential inefficiency of the trace in order to reap the benefits of compaction, or accept increased memory usage in order to have more efficient traces. Ultimately, we didn't ship compaction of dynamic objects in Diablo IV, instead opting to refit the BVHs to take advantage of increased trace efficiency. I think, though, that in the future it is still valuable to explore schemes in which the BVH is periodically refit and recompacted that strikes a balance between trace efficiency and the cost of reallocating and copying the structures. Certainly, paging memory makes the allocation a very cheap operation, and therefore I think that this is a possible future work. So summing up our journey through the implementation, the key takeaways are that the architecture was initially heavily influenced by the design of the existing architecture of the engine, and this didn't necessarily make it the most efficient or the most maintainable. The design evolved over time from the pressures uncovered by the prototype and was informed by optimization efforts. And as the design was iterated on, it became easier and easier to try new and different things to see how they affected performance. The refactoring we went through led to an architecture that I believe is a solid foundation for BVH management, and which isn't necessarily specific to Diablo IV's overall design, save for the quirk of our many-to-one child-to-parent BVH class layout. A singular BVH struct that refers to paged memory and tracks internal state like compaction is intuitive to work with, encapsulated well so that low-level management changes like compaction are invisible to higher-level systems utilizing the BVH. It's memory efficient, and it's flexible regarding when it is created and destroyed. So now we'll talk for a bit about how we preserve the core visuals of the game. Without ray tracing available in all our SKUs, and given that the feature would be releasing after the game had shipped, we didn't have the liberty of recreating any assets specifically for ray tracing or heavily modifying existing content to support the feature. This has a big impact on the decision-making for our feature set and implementation. Some considerations would have to be made when looking at how ray tracing would impact a frame. One very good example of this is reflections. Diablo is a top-down game, so the majority of visual contribution from reflections is going to come from the ground. However, reflections are also add a lot of visual noise, and in the game without ray tracing were generally considered undesirable because of this extra noise. It was a gameplay decision to limit them. So the materials on the ground and other surfaces like water intentionally modify reflectivity away from a physically based value, which has a downstream effect on a feature like ray tracing, which would use such a value to determine the overall contribution of a reflected ray. We chose to accept the added visual depth that reflections add to some ground materials because it just looks really, really good. But it does incorporate some of the same reflectivity and Fresnel adjustments, pictured to some degree here, that art controls to tweak screen space reflections. And with shadows, an upside is that light leaking artifacts are fixed, which was one of Art's favorite aspects of the implementation. Here we can see a scene where there are several light leaks in the raster version of the game, which are fixed when ray tracing is on. Again, light leaking, fixed. But changes to the shape and hardness of shadows are a departure from the look of the raster game, and so a bit in opposition to the idea of keeping the overall look the same. Now, fortunately, Art did like the effect on these shadows, so these differences were considered acceptable. And a final benefit afforded to us by ray tracing has to do with the number of shadows overall that we can support. With raster shadows, we are limited by the number of shadow maps that we can capture at any given time, or even cache away for use later. The game attempts to promote some lights to dynamic casters when it can, which depends on proximity as well as overall contribution to the frame. And as a result of this, enough lights in one area can create some popping, as seen in this video here. Now, spotting these artifacts in real content is harder because our artists go through great efforts to avoid these scenarios, but they do happen sometimes. By ray tracing every eligible light, we can get smooth, continuous shadows while moving from one light to the next, eliminating the popping. Then there are a lot of scenarios where content in the game simply can't be ray traced. We have two prominent examples of this: vertex animated textures and the player character. Vertex animated textures bake simulations, usually from Houdini, into textures that can be played back via a vertex shader. This was one here that you just saw. Since ray tracing APIs do not offer a way to manipulate vertex positions as part of the pipeline, for obvious reasons, this means that the results of any vertex animation need to be pre-computed and stored before being pushed as an update to an acceleration structure. Indeed, we did this for foliage and skin characters, but after a lot of consideration on the potential impact to memory and time required to fully support them, VATs were considered out of scope and cost prohibitive. For the player character, there is no problem including the character in ray-traced directional shadows, but shadowing from the player light is a bit more complicated. Artistic direction on the mechanics of the player light led us much earlier in development to a solution that warps the player shadow so it does not appear to be shadowed directly from above where the light is located, but instead from in front. This warping is done, you guessed it, in a vertex shader. So I want you to pay close attention to the shadow of the player in the top right. Instead of pre-computing this result as we would need to, the character is simply excluded from the ray tracing of the player light, and a PCSS filter is used on the rasterized version of the shadow in order to fit it closer visually to the other ray trace shadows around it. And the result is pretty close. These exclusions meant we needed a robust system for deciding during scene gather whether an object should be included in a ray tracing technique or whether it should fall back to rasterization techniques. The solution we came up with is what we call hybrid rendering. It exists for shadows, but not so much for reflections. For reflections, the object simply doesn't appear in the reflected scene, and for the most part, it's not as apparent. At a high level, every renderable base type in the engine defines a series of functions which evaluate an instance of that type for inclusion in different ray tracing techniques. Now, things get more complicated when we consider post-process techniques like volumetric fog. Volumetric fog relies heavily on raster shadow results, particularly to help determine interior versus exterior spaces. If that information is not straight, you can get dense fogging in interiors, like this. The trouble here is that the roof of the building appearing in the directional shadow map is what helps the fog algorithm determine that it's operating in this interior space. But since the roof can't be ray traced, it no longer appears in that, or since the roof can be ray traced, it no longer appears in that raster shadow map. And with the ray trace shadow map being screen space, it's ineligible to be used in the fog algorithm. It represents results, not obstructions. One very obvious approach here is to ray trace the fog too. And yes, this would work, but it was work we could not afford to invest in given the complexities of the impact that it would have on performance, like that it would be required to run on top of even the lowest tier of ray traced shadows being turned on. There are also techniques like light transmission that we support, which were only designed to work with raster shadow maps. So we have a situation where most objects are eligible to have ray trace shadows, some objects are not, and some features still require complete raster shadow maps to function. To solve this, we had to create perhaps our most complex high-level system in our ray tracing implementation, which we call hybrid shadows. Our end goal here is to have three maps: the ray trace shadow map for a light, a shadow map of non-ray traced objects, and a shadow map of all objects. To assemble these, we classify each object casting a shadow in the scene. An object is considered hybrid if it's included in any of the ray trace shadows techniques. That is, it is ray traced, but it will still need to appear in a raster map too. An object is considered non-hybrid if it is not ray traced at all, and therefore only appears in a raster shadow map. I'm not going to include details here like how static shadow maps and treatment of static versus dynamic objects affects this system, as that would take up a bit more time than we have. After classifying objects, we raster both of the categories. First, we raster hybrid objects into one map, then we raster non-hybrid objects into a different map, and finally, both of these shadow maps are combined in a custom shader. Later, during deferred lighting when we render a light, if the light is ray traced, we combine the ray trace shadow map, the raster shadow map of non-hybrid objects, and finally, the combined shadow map. A traditional shadow sample is a min operation between the ray traced map and the non-hybrid raster map. For materials using light transmission, the combined shadow map can be sampled in the shader as well. And likewise, for any non-ray traced light or for volumetrics, only the combined shadow map needs to be sampled in this case. Now, it's true that overall, this scheme requires all shadows to be rastered out as they were, with ray trace shadows being purely additive. But this was the cost of maintaining these existing rendering techniques, and can thus be seen as a cost to be absorbed when integrating ray tracing into a rendering engine that wasn't originally designed for it, which seems like a really nice segue into our conclusions. So, summing up, clearly introducing ray tracing has a big impact on our technology and how we think about its future. But what about our players? I think it's important for us to take an honest look at the cost-benefit of the features from a player perspective. Yes, ray tracing eliminated many shadow artifacts and gave us an excellent visual boost in areas of the game with reflective surfaces. But in this engine, it also has a relatively high cost, and people don't always like that for what they might consider as a minimal visual gain. The things we look at as graphics programmers or artists tend to be more detailed, more nuanced than what a player might see. This tells me that there are perhaps better areas of application for the technology which can increase visual impact, but in turn would require greater investment and further consideration of ray tracing in our artistic direction. The potential is out there. The next step isn't so much of a step as it is a leap forward into embracing it. Technologically speaking, I think it's interesting how, as I hope I've demonstrated here, the conceptual idea of fitting ray tracing into a game not designed or art directed for it actually permeates down into the technology, as above, so below, in a manner of speaking. We find ourselves with architectural patterns that sometimes work against the shift in paradigms that ray tracing introduces. And finally, the foundational work of ray tracing is not to be underestimated. Having a robust foundation is central to any successful technological effort, and this is no different. It can, will, and did take up a large bulk of the work. Once that foundation is in place, more opportunities open up to explore new applications and techniques that will have greater impact on the game. I would like to take the opportunity to thank all of the many people who contributed in some way, large or small, to bring ray tracing to Diablo IV, as well as those who helped create this talk and gave feedback on it. And of course, a big thank you to the conference organizers, Michael, Natalia, Stephen, Angelo, and Stephanie, for putting together another great iteration of REAC. And at this time, I will hand it over to Kevin to answer any questions. Thank you so much for listening. Ask away.
Thanks very much, Kevin. And now handing it over to another Kevin, who's joining us.
Hi.
Thanks, Kevin, for joining us. I'm going to start off with a question from Adam Mars, which is around incremental PSO building. How did you guys handle it? When they weren't, when the PSOs weren't ready for the ray tracing, did you just skip PSO entirely and fall back to raster? Did you have some sort of visual pop that you just ignored? Like, what was the handling for that?
Yeah, if the PSO isn't ready at all, we do fall back on raster techniques. So SSR for reflection as an example. But if we have a PSO that exists that we update live, we live with the actual popping. The add to state object function call works very well. The character speed isn't that high, so we don't run into that issue that often. So, yeah.
Got it. Thank you. And I'm gonna bundle a couple questions here from Govid Vendikash, Karim Lucin, Alper Ozkin, and Volkan Iveli to kind of talk about the speed tree issue, which I feel like has been percolating in Discord in a couple of different dimensions. One, pardon me, how you handled alpha mask geometry, if at all, how your any hit shaders, if you did use those, impacted your performance impact, because there's a comment that outdoor scenes were actually more performant in some cases. What would you guys like to change about your foliage handling? And there's a corollary question, which is just around, I think, transparencies and volumetrics in general, where Karim asks, RFX stuff included in ray tracing, which I'm going to assume is a question around participating media and things like that. But let's start with kind of just more thoughts around speed tree, how it was handled, and what you might like to do differently.
Right. Yeah, we are not doing anything fancy yet. So the approach is very naive, I would say. So for foliage, everything is animated every frame. So we at the beginning of the frame, we pre-scan everything. They are all unique instances, so there's not much reuse. And our leaves are simply alpha-tested, so tons and tons of any shader activity. So it's very expensive. Why? And that's why it's a dedicated option on PC and not enabled on console. Something we would like to do moving forward is maybe like experiment with tighter geometry for the leaves based on alpha values. I mean, that would mean that traversal and memory usage would be higher, but we expect there would be an overall win. There's a thing with the NVIDIA micromap that seems interesting, something we'd like to experiment with. More inline ray tracing, I think, with performance, more instancing in general. Every tree doesn't have to be unique. So yeah, this is something we really need to invest in. For the VFX side of things, yes, we retrace them, but reflections only. Every frame we rebuild to be last for them. To help with performance, we call small things like items. And if I remember correctly, we're not doing anything fancy to properly support camera line billboards. And because reflection, they don't contribute that much. It's not something that is very visible, so we can get away with that. Yeah.
Understood. Great, thank you. Moving to a question from Cleo H. Niori. Yes, I can see how you might only care about reflections to the floor when you have a normal play camera view, but what happens at cutscenes? Do you just not have reflecting materials outside of the floor and they're mirror-like? And I think this is a really interesting question too. Just, I mean, you know, I think you could do a whole other talk on Diablo. What does it mean that it's not a first-person shooter? For many of us who are so used to that, thinking about how different that perspective for your camera and things like that is. But at the same time, D4 does have in, you know, some of those swoop cut scenes, right, when you're playing through the campaign and stuff like that, which, you know, we're all playing seasonal now, but still, I'm sure you have to support it. So,
yeah. I mean, like you mentioned, we do have like real-time cinematics, and I think they're called point of view, point of interest, where the camera angle changes, and you can see like in the background. So we didn't want to do any assumptions. So we're not doing any top-down specific optimizations, and we prefer to optimize for the general case. But yeah, something to explore for the future for sure, because we do have like a good case where everything is controlled, but we don't leverage that yet.
got it. And then I get some specific low-level questions. Dan Moody asks, unless I missed it being mentioned in the talk, what's the specific solution you have for allowing so many occlusion masks? I understand some engines actually generate one occlusion mask per light, others do not. What did you use?
If I understand the question correctly, it's about how we dispatch the different like object and items to different dispatch lists. This is a CPU side thing. We're not talking about like occlusion mask or occlusion queries at all. So it's just like on the CPU, we have different buckets of objects, and based on the object type, we bundle them and then we dispatch the proper passes.
Got it. Thank you. And there are a couple questions around BVH and memory use. You know, Sean Bellet asks, are there times when the BVH data goes over the initially allocated space? Like, how are you handling, you know, kind of your heat management? And then Kareem Lucen asks, was there a similar, you know, vendor extension for memory usage on AMD? Although they later looked up and saw that RTX MU does work on AMD. I don't know if you guys did any sort of like vendor specific testing for this sort of stuff. But I wonder you can speak a little bit about, you know, your heat management, how few triangles, or, you know, like what's your general triangle count per blast, if that's managed at all, if it's all over the place. We can talk about that.
Yeah. Okay. If we go above the initially allocated space, not really. We don't have a fixed memory pool, so we allocate what we need on demand. If we were to go above that, it would mean like hard memory crash, and we don't run into those in retail game. That wasn't the case in that development. That's why we spent that much time on memory management. About the RTX MU library we use, it doesn't use any NVIDIA specific extension or TECT. So it works across all platforms, all vendors, and at one point we had it working on console. I think think there's another point about how we manage fragmentation. I think.
Yeah, fragmentation. I think I don't know if you have a sense of like your average, triangle payload for blasts. Was also a question.
Yeah, in terms of triangle, it can go from like a dozen of triangles to thousands, but I don't have like the exact numbers in front of me. But the thing is, our own memory allocator is based on fixed allocation that we pool. So just with that, we don't run into fragmentation issues. And with the RTX-MU library, it's an issue. They don't do any fancy thing to control fragmentation, and this is something they are actively exploring. So if there's any interest, you can reach out to NVIDIA, and they'll be happy to hear your needs.
Great. Well, I think we're at time. Thank you so much again for joining us and filling in for Kevin. And there are some extra questions in the Discord that I'm sure the presenters will be happy to get to. But thank you very much, Kevin.
Thank you. Bye.
So we're going to shift into our end of show, end of day one material here. I don't know if the presenters wanted to join me, if I'm going to be doing this solo, but let's find out. So thank you again for joining us here on day one of REAC 2024. Talking a little bit about tomorrow and what's been happening. We hope you've enjoyed today's presentations. And of course, if for some reason you haven't joined the Discord today, you missed a lot of fun. There's a lot of lovely memes and conversation, chatter, and catharsis as we shared as we're calling it, pain-based development that is game development sometimes. So if you're on the Discord, you can hop back on to it and read through all the conversation and see all the extra questions that we didn't get to. So please do that. Numerous people have asked when slides and videos will be posted, and the answer is sometime in the near future. So it'll take us a little bit of time to get that. We don't have any firm dates, but you can be assured that when we do have them ready, you'll be able to access them at enginearchitecture.org, as well as on our YouTube channel, which you can see below there. That's that. There we go. So our program for June 4th for tomorrow. We'll start at 8 a.m. Pacific again with our opening presentation with more lovely chiptunes and things like that. And then at 8:15, we'll have Tato Altu from Remedy Entertainment talking about modernizing geometry rendering in Alan Wake 2. Then after a short break, we'll be back at 9:30 with Simon Eschbach with Q&A handled by Stephen White, both of Sledgehammer Games, and both, I believe, in Australia. So I think Stephen's going to be up at 4 a.m. Talking about optimizing the UI CPU-bound frame rate in Call of Duty. And then after our second break, we'll come back at 10:45 with Stephen McCauley and Matt Patinio of Santa Monica Studio to discuss Maya's editor, the game development approach of Santa Monica Studio. And then we'll close up with some wrap up and some thanks. So we'll have a survey ready for you. You can queue it up right now if you'd like to jot down your thoughts, but please don't submit it until end of day tomorrow when you've been able to see all of the presentations and give feedback on all of them. We very much appreciate that. And that's it for day one of REAC 2024. We'll see you all tomorrow at 8 a.m. Pacific. Thank you so much.